The release of Python 3.13 brought the language so much closer to achieving proper 3-threaded support by starting the process of removing the GIL. Now this is the first version, so that's not all quite finished yet, but I wanted to know what sort of effect that had on performance so far. Or in other words, is Python's free threading mode actually faster? And the answer is sometimes. It kind of depends on what you're trying to do with it, and that makes sense at a glance, but there are some surprising instances, or at least there was one surprising instance I found where it should have been quicker, but it was actually slower. In this video, we'll be running over the general circumstances in which it's faster and which it's slower, and you'll learn about the weird thing that I ran into. I've actually been doing some learning myself recently using this video sponsor, Skillshare. Skillshare is an online learning community with thousands of classes led by industry experts in fields such as writing, design, content creation, and more. Maybe I should have a look into that last one, actually. But if you're looking to add to your skills portfolio, want to take your career to the next step, or are just looking for something to learn for fun, Skillshare has you covered. As you may know, if you saw my community post, one of my New Year's resolutions is to learn a lower level language. And to get things going, I've been watching Nathan Stocks' Ultimate Rust Crash Course. This class starts with all the basics, such as setting up projects and defining variables, and ramps up into more complicated topics such as borrowing and ownership. Finally, it all culminates with the development of a little terminal-based game, which I'm really excited for. In fact, as you can see, I've already taken a quick peek. The first 500 people to use my link in the description get 1 month free trial for Skillshare. So if you've got anything you're planning to learn as a New Year's resolution, this is the perfect opportunity to go and actually do it. Go on, you know you want to. While we're here, let's learn all about the performance implications of Python 3.13's free threading mode. So this video is going to take the form of a discussion piece, I guess, more than anything. I'm going to show you how I planned this, what I guess originally wanted to show off, and how it ended up going. So I started with the problem of estimating pi using the Monte Carlo simulation. For those that don't know what the Monte Carlo simulation is, you effectively draw a square and you draw a circle inside it such that the height and the width of the circle is the same as that of the square. And then you plot a series of points within the square, and you can calculate the value of pi relative to the number of points that landed in the circle. And that gives you a good estimate. So something that requires some numerical computation. You have to generate some random coordinates, and you have to do you have to work out whether it's in the circle, and at the end you have to do this calculation here. Simple enough, shouldn't be that bad. We also have a parallelized version here. So this bit is the same. This bit is sort of like a broker, I guess, of threads. So we're using the thread pool executor. We work out the number of points per thread, in which case we're using 10. And then for each thread, we create a future, and then we get the result of the future as provided by the executor. And then we just run an estimate like that. So we take the sum divided by the length, and then we get the estimate out, and then print it in the same way. For benchmarking, I am using just time.perfcounter.ns. I don't think there's really a need to use time it here, but you can if you want. The code will be available down below if you do want to experiment with it yourself. I'm just using perfcounter.ns because it's easier to explain what I'm trying to do. And then if I load up my terminal here, you can see on the left terminal we have CBR GIL. This is a virtual environment that is based off the normal version of Python 3.13. As we can see here, this CBR no GIL is based on the experimental free threading build of 3.13, and they're both 3.13.1, which is the newest version at time of recording. I've just done these virtual environments largely because Starship doesn't make it obvious when you're using the no GIL version, so I've just done it like that for the sake of making it clear to you. So I have the serial and the parallel here. If we run the pi Monte Carlo serial, the pi over here, and then we get it set up over here. While that's running, we can see that the normal version took 1.553 seconds to run that, and it got a pretty decent estimate. The no-GIL version took about a second longer. This is actually expected because the free threading version in 3.13 does not benefit from the specialized adaptive interpreter that is available to the GIL version. It will in 3.14. It might already in one of the alpha builds. I don't know. But 3.14 will have a no-GIL mode with a specialized adaptive interpreter. That's really difficult to say quickly. Active, and but 3.13 does not. So this is what we would expect to see. If we were to then run the Monte Carlo parallel, we would expect this to run a little bit slower. And in this case, it is just a little bit slower. And this is because of the GIL. The GIL gets in the way of all the multi-threading. I've done videos about this in more detail before, but there are a lot of resources you can go and look at as to why the GIL gets in the way. The short story is it gets in the way. We would expect to see this. If we run Monte Carlo parallel here, you would think in the no GIL mode it would run faster because the GIL isn't getting in the way of all the threads. But if you run it, we see it's definitely taken longer than 1.6 seconds at this point. It's definitely taken longer than 2.5 seconds. It takes 6.8 seconds to run, which caught me by surprise quite a bit, I will say. And I was trying to figure out for ages whether or not it was something that I'd done in the implementation. The original version of the implementation I had actually used as completed here from concurrent.futures. Removing that halved the time it took. For some reason, that really slowed things down. But I just couldn't figure out what was causing it. And I landed on the idea that it could be a problem with the interpreter, maybe. So I wanted to do a bit of a sanity check. And I got this transform function here. So if I load these two up next to each other, from InfoWorld's video on the same topic. And the reason I use this specifically is not because I just wanted to steal. I can actually get rid of this import. Not just because I wanted to steal the code or anything. It's because I wanted to do a sanity check. Because I'd seen this video, I'd seen with my own eyes that the no-GIL version was faster than the GIL version. So if that was the same thing here, then there wasn't a problem with the interpreter. If the no-GIL version was still slower, there was a problem with the interpreter, and that's where the slowdowns were coming from. I will have a link in the description and a link in the cards to that video as well, if you want to watch it, and I recommend you do, because it does talk about some more stuff like multiprocessing and how that gets affected. But if we run this now, serial, and then pi transform serial, get that ready to go. On the GIL version, it takes 6.661 seconds, and on the non-GIL version it should take maybe a bit longer. A little bit longer. Again, differences in the specialized adaptive interpreter that it's not able to use. If we run transform parallel, we see, if I remember correctly, it takes roughly the same amount of time in parallel as it does in serial. Yeah, pretty much exactly the same. If we run it on the no-GIL version in parallel, so this is using the thread executor, it runs a lot quicker. You can see we shave a solid 5 seconds off even the fastest time we got in the GIL version. So it was not a problem in the interpreter. And I will say as well that I did make this parallel transform system as similar as I could to the one I used in the Monte Carlo simulation to try and rule out as many things as possible. So I was looking at the differences between the two, thinking, what could possibly be different about these two? And then I saw this random.random here. So in transform, we are only dealing, I believe, with integers. This random.random generates a float. Whether or not that's important, I don't know. But it also does go and generate a random number. And I was thinking, well, maybe it's the numerical computations that are causing the problem. So if I just do that. So I changed this to be 0.5 for both. Completely breaks the algorithm, unfortunately. But if we do Monte Carlo parallel here on the GIL version, we'll see it takes 1.044 seconds. Gets a pi value of 4. If we do pi Monte Carlo parallel on the no-GIL version, it takes about a fifth of that. Actually, slightly less than a fifth of that. So for whatever reason, it is something to do with random number generation in the no-GIL version of Python. And we can probably put this down to the fact that maybe random number generation just is not optimized to work with no GIL yet. It is still experimental. It even says that in the interpreter. So there's a chance that random number generation or something to do with random number generation does not currently sit well with no GIL, and there hasn't been any work to make something thread safe or anything like that. I don't know what happens if no GIL Python encounters something that isn't thread safe. I imagine it just blocks, which is probably what's happening, and then you get in all these thread management overheads, and that's probably having a massive effect. That is my guess. Unfortunately, I can't really give you much more than that, because I tried profiling it with cProfile and I tried profiling it with PySpy. Neither work with no GIL Python that's running multiple threads at the moment. cProfile will just hang indefinitely. I tried to run it earlier today, and I was waiting for half an hour. I had it running for half an hour, and it did nothing. So that doesn't work. I tried running PySpy, and PySpy complains about not being able to find the target executable. I don't know if that's an issue with PyEnv specifically, but it runs on Linux anyway in different ways with PyEnv, and it's completely fine. So I'm not sure what's going on. There is an open issue saying that it doesn't work on free threaded mode. So I'm kind of betting at the moment that it's not my fault. If you can get it to run with PySpy or any sort of profiler, and you can give me any insight into why random number generation is so slow in no GIL, then do let me know. If you want to send me any images or links, you might have to join the Discord server, because YouTube comments will get rid of links and stuff. Again, code will be in the description if you want to play around for yourself. But this video, I guess, serves as a bit of a notice to say that it is very much experimental still. It is not a magic wand as yet. No one really expected it to be. Well, I say that. There may have been people who expected it to be, which is kind of why I'm making this video like I'm making it. But do very much keep the use case in mind, and just keep in mind that the feature is still experimental. For the sake of it as well, I did actually go ahead and construct a Numpy version of the Monte Carlo simulation, which looks like this. And if we were to run that, say in this one, so Monte Carlo with Numpy, that runs stupidly fast. That runs at 0.191 seconds, and you get a decent estimate on Pi. If you run it in the no GIL one, I don't know if it actually has an effect at all. No, it's slightly... Oh, it's wrong. Oh, I've run the wrong one. That's what... That would help if I actually run the right file. Yeah, it's slightly quicker. I wonder if no GIL... Oh, that's 1.32. That's 1.2. It's getting faster and faster. 1.22, 1.23... Yeah, I think it's converging on about the same amount of time. So it's about the same time. Numpy doesn't seem to have an effect. Let me know in the comments if you have experimented with the free threading mode yourself, and what you found in experiments, like what situations it does work well in, what situations it doesn't. And if you found something similar to me, where having something multi-threaded doesn't necessarily mean it's going to be faster, and actually could potentially be much, much slower. As part of the ongoing coverage for Python's 3.13 and 3.14, I will have more videos as things happen about the GIL and about no GIL modes and all of that stuff. So if you are interested in following the progress of the free threaded mode, then do subscribe to the channel, and you'll get all those updates straight to your sub boxes. If you want to see other ways in which you can make Python faster, a lot of them are a bit more reliable than free threading mode at the moment, then you can look at the Python but faster series in the end cards. And I'll see you in the next one for whatever we do next.